Okay, well, I just wanted to take some time this morning to put up another video regarding the production sheet for Betty's Bats, the final deliverable for Management 251. So let me start by screen sharing the production sheet. You will find the production sheet in contents on Blackboard shortly after I'm done with the video. And as I mentioned in several video sessions so far, the final deliverable incorporates at least three powerful tools of the OPPM course: OPPM, Operations, Production, Project Management, all of which are crucial to our understanding of management, management behaviors, management tools, incorporating different devices, different tools, different mechanisms that we will use invariably in each of the three areas, whether it's in operations management, production management, or project management. So I mentioned the three that we were uniformly going to use this semester, and the first section was forecasting. And which technique? Well, we've learned several, so you will have the choice in Betty's Bats to choose a very simple technique like moving average, or a little bit more elaborate technique, more robust, arguably, like exponential smoothing, linear trend line, and so forth. Second area had to do with Frank's Fine Floats, and by now, hopefully, you've reviewed Frank's Fine Floats, played with it a little bit, and understand what it's about. And hopefully, you took the tasking to heart. And whether you decided to bake a cake, change a tire, do whatever, water the garden, cut the grass, whatever it was, hopefully you were able to apply that and come up with a critical path and understand from your study of the PowerPoints and referring to a textbook or the internet, whichever was more convenient for you, and be able to understand, look, this is how I implement it. This is what slack time is. Now I understand the idea of prioritization, the idea of slack time, and so forth. Hopefully that's pretty much a tool for you. And that will be an area that we'll use here in the production of Betty's Bats as well. The third area is the optimization area, and we have not yet played with that. And that will be for the last week of class. And I will probably post videos later this week so that next week you can go through the 2 or 3 or 4 videos that I will post regarding optimization and using Microsoft Solver. So today, let's just talk about the Betty's Bats production sheet. So if you observe, and again, you can go to contents after this video, after viewing it, or even while you're viewing it, and open this on contents in Blackboard. You see, the first thing we start with is a 5-year forecast. Okay. So again, what we're making, what we're producing, in this case, arguably on a production basis, but it easily could be a standalone single term project basis. What we're making is baseball bats, aluminum baseball bats. We use them in Little League, softball, whatever it happens to be. So Betty's Bats. Whatever year, their first year, Betty's Bats produced, and again, we talk about forecasting using demand data and so forth. Well, what we have is, in essence, 5 periods of demand data. The actual demand. Year 1, Betty's Bats actually made 875,000 bats. Year 2, Betty's Bats actually made 920,000 bats. Year 3, a million, so on and so forth. So we're trying to forecast this next year, year 6. What will we produce in year 6? We look at the actual demand data. And even if we did something very simple, sum divided by number, in other words, a 5-period moving average, Or if we only took the three most recent data points, 3-period moving average, we would sit back and say, okay, well, let's see. Since the largest number is a million and I'm averaging some smaller numbers in there, right out of the box, I know I'm going to produce something short of a million bats. Well, first thing you're going to have to do is choose your technique and come up with a production number, a forecast number, which will be our production number in an effort to meet what will ultimately turn out to be the actual demand for year 6. But of course, when will we know this? We'll know the actual demand number at the end of year 6. So we're forecasting what's going to happen in year 6. So we're going to take all of this and whatever technique we apply, 3-period moving average, 5-period moving average, 3-period weighted moving average, exponential smoothing, adjusted expo, all these techniques that we've studied a little bit, we're going to pick one of them and we're going to come up with a forecast number. After we have the forecast number, one thing we haven't spent a lot of time talking about is the idea of throughput. And whether it's a project basis, as in Frank's Fine Floats, where our throughput is, one unit that we've ultimately got to build, or whether it's on a production basis where our throughput is a little bit more constant. Think of, the automotive assembly line, whether it's Tesla or Ford, whomever, it is, that doesn't matter as much. Throughput. In World War II, and that's even history to me, as odd as it may seem, certainly history book stuff to you, but in World War II, there was something on YouTube that I watched several years back that said that this thing they called a Liberty ship, and it was kind of a really cheaply built kind of supply ship to get goods and arguably sometimes people, but mostly goods from point A, presumably, the North American continent, to Europe, specifically the UK, but other places as well. And so these ships, at the height of production in World War II, the shipyards turned out one completed Liberty ship per week. Can you imagine? Can you imagine? Right, it's not a 115,000 ton displacement cruise ship, but it's a ship nonetheless. I mean, you're starting with steel, got to be welded and or riveted. You're talking about piping. You're talking about motorizing this thing. You're talking about a lot of wiring, cabling, and electrical stuff, electronic stuff, all of this stuff. And they turned out, excuse me, a ship a year or ship a week. How'd they do that? Well, it's not what it may seem right off the bat. If we stop and think, could a hardworking group of folks actually slap this thing together? Well, the answer is no. But what it kind of means is that, like a car on an assembly line, it starts with something, some bent piece of steel, and it moves down, and at the next station they add whatever they add to it, and it goes down another station and they add something else, and then eventually, it's the doors and the seats and the motor and the radio and the blah blah blah. By the time it gets to the end of the assembly line, and a finished car is basically spit out the back end. Well, once that queue is full, you're probably producing a completed vehicle every, I don't know what it is, every 20 minutes, every 15 minutes, every half hour, a finished car comes off. And so you say, well, geez, how long did it take to build that car? Well, we get a car off the end of the assembly line every 15 minutes. Well, in one sense, we've spit out a completed car in 15 minutes or 20 minutes or 30, whatever that number is. Well, it's the same with the Liberty ships. Once the queue is full, so you got to lay the keel, and then somebody else has to cut and weld the ribs, and somebody else has to weld or rivet steel onto it. And eventually, you get the idea. So each step but while we're done with the keel here, we start another keel here. When we're done with that keel, we start another and another and another and another, to the point where we've got this queue of Liberty ships, each in a different state of completion, each state or each stage or each operation or each activity being one more step to completion, nearer to completion. Well, then eventually it's done. And the one behind it is almost done, and eventually it's done, and the one behind, and so forth. That's what we're talking about. So part of it is that critical path stuff. So when we talk about throughput and using this idea of critical path, look at what we're doing here. In Betty's Bats, we have activities A through E. Now, is that real? No, of course not. We're not an engineering school. We're not really building or designing a baseball bat. But for our purposes, Betty's Bats, these are the activities. Now, you'll remember in Frank's Fine Floats, it was A through H. There were several more activities than we're listing here. And we could make this tens of thousands of activities. We're centering around 5. All right. It's a classroom example. It's not real, but it's real enough for us to understand what we're trying to understand here, which is the idea of process and the idea of throughput and the idea of critical path and so forth. I mentioned to you at another point in time that if you master Frank's Fine Floats, at least sufficiently, and you go to apply that here, stage 2 of our project, to Betty's Bats, this will be a bit easier and a heck of a lot more linear. Now, I'm not going to do the project for you, but remember those words. So let's look at this. What are the activities, the prioritization of activities? And remember from Frank's Fine Floats, first you had to do the paperwork, and before you could do B or whatever it was, A had to be done, and before you could do C, A and B had to be, blah, blah, blah. Okay. First activity is slugging, and it takes 3 minutes. You know what slugging is? Doesn't matter. You don't need to know. All you need to know is that activity A, it's got some kind of a name which is kind of meaningless to us, and it takes 3 minutes. Next activity, activity B, first extrusion. Do we know what extrusion is? Doesn't matter. It's just a name. We're not an engineering school. We're not really extruding anything. Activity B, first extrusion, takes 2.5 minutes. Activity C, second extrusion, takes 4 minutes. Activity D, finishing, which actually encompasses a whole bunch of activities, but we're not really doing a baseball bat, so it doesn't really matter. Activity E, instead of what would really happen. So between activity A and activity B, this part or parts would have to be moved from A to B, from B to C, from C, and so forth. Well, instead of actually mapping that out and complicating our, and again, remember the nodes and the arcs and okay, so instead of complicating Frank's Fine Floats, we're simply going to call it activity E, and what it says is we're adding a minute of time to our overall process. So let's look at our throughput. In cars, after the queue is full, we spit out an automobile every whatever it is, 15, 20 minutes. In Liberty ships, after the queue is filled or full, we spit out a Liberty ship once every week. In terms of Betty's bats, look at the activities. One's 3 minutes long, one's 2.5 minutes long, one is 4 minutes long, one is 3.5 minutes long, and then we're adding a minute to each. Or actually a minute in the aggregate, not to each activity, but to each bat. What's the longest activity here? 4 minutes, second extrusion. Add a minute to that because that's what we said we were going to do. So after the queue, each of these stations, and there are really 4 of them, but after each of these stations is filled, how long does it take to spit out a finished bat? 5 minutes. The longest individual activity time, or cycle time if you prefer. And we said we're adding a minute to that. So 4 plus 1, do the math, is 5. Every 5 minutes, we spit out a finished baseball bat once the queue is filled. Now, it kind of makes sense. Think about it. Ever watch Krispy Kreme? You know, the donuts, they get mixed and they get this, and the machine then cuts them and puts them on the conveyor, goes and puts them in the fryer and flips them and all of this. Well, whatever the throughput is, every, I don't know how long it takes, 10 minutes, you've got a whole tray full of fresh donuts. Well, it's the same kind of thing, same as the ships, same as the cars, same as anything else. And for services too, think about it. You have an operation that does CAT scans or x-rays or whatever it is. Let's say it takes 20 minutes to do a CAT scan or an MRI or whatever it happens to be. You add 10 minutes for, people fumbling around, going here, take your clothes off, put on this gown, stand over here, come in over, all this crap. So 10 minutes there. So add the 10 minutes to each CAT scan or MRI, which is 20 minutes. So now you've got 30 minutes. So every 30 minutes, you have a completed MRI or CAT scan throughput. And that's what we're talking about. So we're going to forecast, we're going to come up with a number, and then we're going to sit back and say, look, accepting the handling time, once the queue is full, you produce a bat every 5 minutes. Okay. So let's look at what that means to us. If we have to produce, because we forecast up here, if we have to produce something just short of 1 million bats, just short of 1 million bats, whatever your number is from your forecast, you have to produce in a year that many bats. And we now know that it takes 5 minutes to make a completed bat, once the queue is full, but 5 minutes per bat. Well, our model is this. We have 3 manufacturing plants, 3 big buildings that has the machinery to do all this stuff we're talking about. Each plant has 6 production lines. So one production line would be, slugging, first extrusion, second extrusion, finishing. Okay, that's one production line. So if we have one next to it, slugging, first extrusion, second extrusion, and one next to it, slugging, first, and 3 more next to it. We have 6 production lines that slug, that extrude again, that finish, and then we said we add, a minute to each thing. So let's start to think in terms of some numbers. 6 production lines, and for our argument, this is our production sheet. For our argument, not our argument. Anyway, our argument, 50 production weeks a year, 40 hours per week, times 50 weeks. Now that's one shift, one production line, equals 2,000 hours. But since we've broken it down into minutes, so break this down into minutes, or 120,000 minutes. So if we have 120,000 minutes available, divide that by 5 minutes per bat, that gives us 24,000 bats per shift per line per year. How many bats we need? Almost a million. Well, one shift, one line, 40-hour work week, 50 weeks of production ain't enough. What about 3 shifts? So we take this 24,000 times 3 and we end up with 72,000 bats. 72,000 bats times 6 production lines equals 432,000 bats. Is that enough? Nope. Why? Because we know up here from doing the math that we need almost a million bats. Okay, so 3 shifts instead of 1, 6 production lines instead of 1. How about 3 manufacturing plants? So 432,000 bats times 3 manufacturing plants, each of which has 6 lines and 3 shifts and all the stuff we put in here. And we have basically just about 1.3 million bats can be produced. Means that what? That we can meet our production requirements, that there is excess capacity we won't be using, but that is what the capacity is. So we have 3 storage/inventory facilities. Why? Well, because that's what we have. So we have 1 warehouse that can handle 350,000 bats. We have 1 that can handle 500,000 bats. And we have 3 that can handle 450,000 bats. So 1 can do this, warehouse 2 can do that, warehouse 3 can do that. It's not 3 warehouses with 450. It's this one handles that, this one handles that, this one handles that. So what are we concerned with? Well, in any operation, and when we look at the optimization and the examples we're going to go through, this will make a little bit more sense. But when we look at optimization, we're either trying to always maximize something or minimize something. We want to maximize profits, for example. We want to minimize costs, for example. Well, in this case, we're trying to minimize, and this is the third part of Betty's Bats, the third piece, which is optimization using Microsoft Solver. That's our tool. So we've got 3 production facilities. Remember we said that? We have 3 plants, production facilities. Each has 6 lines, each does 3 shifts, blah, blah, blah. And we have 3 warehouses, which can handle inventory and storage, packaging, whatever they would do, of dissimilar amounts. So the question ensues, well, I have to, from each of the 3 production facilities, transport all of these bats to one of the 3 warehouses. Only they don't have the capacity to store all of the bats. So it's kind of got to be broken up. Now, there are different mileages, different distances from each manufacturing plant to each warehouse. For example, plant 1 to warehouse 1 is 6 miles. Plant 1 to warehouse 2 is 19 miles. Plant 1 to warehouse 3 is 22 miles. Plant 2 to warehouse 1, 19 miles. Plant 2 to warehouse 2, 18, and so on and so forth. Dissimilar mileages. What's our optimization strategy here? To minimize costs. We minimize costs by minimizing transportation miles. In the current context of runaway inflation, or arguably so, and on top of all the other supply chain issues and so forth, fuel costs being injected into the calculus, we understand that minimizing transportation miles, optimizing that as best we can, is hugely important. So we're trying to minimize transportation miles, or as I phrase it in the context of this example, we are trying to minimize bat miles. So to minimize bat miles, we will be using our third example from class. There will be three. We have not gotten there yet. The first one will be a simple one, the second one a bit more robust, and the third one will be something entitled Tropic Sun. And when we go through that, you will see the similarity between Tropic Sun and this Betty's Bats part 3 of the production sheet. Your job will be to, in essence, overlay what you pick up and learn here to resolve what you see here. And ultimately, that is your final deliverable. Let me stop share. Okay, so that is the production sheet for Betty's Bats. That is your final deliverable. So we will be putting up a quiz very soon on forecasting, maybe even later today. There will be another quiz on critical path, and that'll probably be by the weekend. And then your final deliverable is Betty's Bats. I've just gone through the production sheet with you. I will try and be here on Friday if, weather and internet, and, as I refer to it, the Tron God, electronics, Tron. If the Tron God is good to me and we have, internet and power and all these things, the confluence of essentials that has to come together. If that comes together, then we will meet on Friday. So join us at the voluntary Zoom. It's absolutely voluntary if you choose to, and I can answer some questions for you. All right, with that, I'm going to end the video. Enjoy your day. I hope you understand what we're saying here. I am going to post this production sheet to Blackboard Contents as soon as I sign off here. Stay safe. We still have all kinds of that. Now there's a new thing, monkeypox or some damn thing. What the hell is that about? Anyway, there's all kinds of stuff to be concerned with. Stay safe, stay healthy. Your health and everything comes first. Family comes first. And we'll chat soon. Enjoy your day.